Good morning. I can see that there are less students in class today, but still it's time, so we are starting. Okay, so today's topic is elasticity and viscosity. Okay, so even though it's a very small topic, okay, elasticity is also a small topic, viscosity also is a small topic, but you can see that how many questions have been asked in the previous year. Okay, let's see. In this we will be covering the topics stress, strain, modulus of elasticity, Hooke's law, that is from elasticity part, and from viscosity like coefficient of viscosity and terminal velocity. Okay, let's get into the chapter without any delay. First, when we talk about like stress and strain, like we need to know what is stress. Okay, stress is nothing but force by area. Okay, force or load. In this we are dealing with three types of stress and three types of strain, and also three types of elasticity. Okay, modulus of elasticity. First one, we are dealing with longitudinal stress and longitudinal strain, which means like the stress is applied perpendicular to something. Okay, and because of that stress or because of that force, elongation is happening, like lengthwise change is happening. That is why it is called as longitudinal stress and longitudinal strain. As you can see here, the force is perpendicular to the area of cross section. Okay, so stress will be this external force applied by area of cross section. Now strain which is happening, stress we generally represent using Greek letter sigma. Okay, sigma means stress in this chapter and epsilon is strain. Okay, and strain we can calculate by change in length divided by original length. So instead of this you can also write as delta L by L. So when elongation is happening, how much extra length is there divided by original length, that is stress, longitudinal stress and longitudinal strain. I hope like you guys understood this. Can we move to the next then? Okay, coming to next, that is shear stress and strain. Shear stress, the force is applied tangential to the surface. As you can see here, this is the direction of force. Okay, so there is a surface and force is acting tangential to it. That type of force is called like tangential force, and because of that tangential stress is there. Again, equation is same, F by A. So whichever surface the force is acting on, that is our area of cross section. Okay, so again stress, tangential stress force by area of cross section, you will get shear stress. Now shear strain, that we will find in a different way, not by elongation or anything. As you can see, when a tangential force is applied, there is a shape change happening in the object, right? So force is applied in this direction, so a shape change happened, and they have mentioned this angle as, here it is gamma, usually we can mention as phi also. Okay, and if you take tan phi will be equal to this opposite by adjacent, that will be our delta L by L only. Okay, that change in shape, but we have to measure, and since the shear strain will be like very less, change in shape and all like won't be that visible to us, it will be a very negligible change, which means angle phi will be very very small. In that case, when phi is very very small, we can say that tan phi is equal to phi, which is equal to delta L by L. Okay, so this is the concept of shear stress and shear strain. Shear stress, force acting parallel or tangential to the surface, stress equal to force by area, no change in equation there. But coming to shear strain, we are actually finding tan phi, but since phi is a very small value, angle is very very small, we can say that tan phi equal to phi, then phi equal to delta L by L. This will be shear strain. Any doubts here? No. Okay, so let's move on. Next is volume stress and volume strain. So here we are actually talking about, let's imagine a balloon. Okay, the atmospheric pressure is acting on the balloon, right? It's acting everywhere on the volume of the balloon. So such a type of force is called as volume force, or like volume stress we can find. So volume stress is nothing but our pressure. Okay, whatever it is there, the pressure we will take and call it as volume stress. Okay, as you know, like atmospheric pressure acting on the balloon, that is the example you should remember. So volume stress is pressure. Then volume strain is nothing but volume strain will be change in volume by original volume. Okay, no changes there. Are we clear about longitudinal stress and strain, shear stress and strain, and volume stress and strain? Is these three concepts clear for you? Okay, so next we need all these three for learning about modulus of elasticity. Okay, coming to modulus of elasticity, we get that by Hooke's law of elasticity. Okay, Hooke's law is stating that when under elastic limit, okay, under elastic limit, stress is proportional to strain. Okay, this is actually the formula of Hooke's law. Under elastic limit, stress is proportional to strain, which means stress by strain should be a constant, right? Should be constant. This constant is what we call as modulus of elasticity or elastic modulus. Young's modulus only in the case of longitudinal, we will come to that, but stress by strain will be a constant under elastic limit, and that constant is called as modulus of elasticity. This is what Hooke's law tells us. Okay, now coming to longitudinal, like if we are taking longitudinal stress and longitudinal strain, we will get by longitudinal strain, we will get Young's modulus. Okay, longitudinal stress by longitudinal strain is Young's modulus. If we substitute things here, we will get F by A, that is longitudinal stress. Strain is delta L by L. So this is the equation for Young's modulus of elasticity. Now if you take shear stress and shear strain, you will get modulus of rigidity. Okay, or rigidity modulus you will get. This is Young's modulus. Next is rigidity modulus, and that we represent using eta. Okay, this eta has multiple names across physics, and each will depend on which chapter we are studying. Here it is modulus of rigidity, and if you come to viscosity, this is coefficient of viscosity. So you should know the difference. Okay, and if you substitute, what is the value we are getting? Again same formula only, A delta L by L, but actually this is F by A phi. Okay, so in both ways you can see, if angle is given, you can just substitute the value also. Is that clear? Okay, now coming to volume stress by volume strain. Okay, volume stress by volume strain, then we will get bulk modulus. Okay, Young's modulus, modulus of rigidity or rigidity modulus. Next is bulk modulus, that we can substitute by volume stress is just pressure and volume strain is delta V by V. Okay, so pressure is inwards. What is happening? Delta V will be negative. Pressure outwards, delta V will be positive. Okay, so that you should keep in mind. So this we will get as P by delta V into V. Now based on this only concept only, bulk modulus, we have so many applications in thermodynamics, kinetic theory and all, because you can see there is PV term here. We can write it as PV equal to nRT, and like further applications we can do. Okay, so this term we won't be using in this chapter much, but we will need it for thermodynamics. Okay, please remember that. Is these three clear for you? Okay, coming to next, this is Hooke's law graph. Okay, stress strain curve we will call it, and if it is not clear for you, I can like slightly, sorry, no need. Okay, as you can see, this is strain. Okay, on x-axis we are plotting strain, on y-axis we are plotting stress. So this is stress versus strain curve. First you can see stress and strain, they are increasing in a linear way, which means when strain is increased, stress is increased, strain is also increasing up to point A. Okay, this is called as, like, this is the region OA. OA is the region where the material will obey Hooke's law. Okay, obeys Hooke's law. Okay, so from O to A, when the graph is linear like a straight line, it will obey Hooke's law. After that you can see from A to B there is a small curve, and till here, okay, they have put like a separate color. Why is that? Because A to B till O to B is the elastic region. Elastic region, which means if you deform something, if you are elongating something, and if you release that force, it will come back to its original shape. That is called as elastic region. Okay, like imagine there is a rubber band, you are pulling it, if you release the force, what will happen? It will come back to original shape. So that much region is called as elastic region. Now what happens if you pull the rubber band very long? It will break, right? So come after this B point, the thing is that it will not come back to its original shape. Okay, this is elastic region, this is plastic region. In plastic region, what will happen? The material will not come back to its original shape. So that's why elastic region ends at B. Then from B to C and all, like B is called as yielding point. Okay, yielding point means maximum we can get back to original shape. Now point C and all, you can see stress and strain will, like if you apply stress, there will be strain, like the shape or like length, everything will change. But what is happening? It will not be proportional. Stress and strain will not be proportional. If I apply little stress, so much strain will come. Okay, like that it will go, and up to point D. Point D is called as ultimate tensile strength. Okay, D, ultimate tensile strength, which means maximum stress it can take. Okay, after that, even if you reduce stress, okay, if we reduce stress also, at some point it will break. That point is E. E is called as fracture point. Okay, so these are the notations in this graph that you should know. First one is point A, that is the like point till Hooke's law is obeyed. Then point B, that is the point till stress is proportional to strain. Till A stress is proportional to strain. Till point B, elastic limit, it will come back to its original shape. Then from point C, what is happening? Stress and strain are not proportional to each other, and also it will not come back to original shape. So plastic region. D is ultimate tensile strength, maximum strength a material can take, and after that if we still reduce the stress also, at some point it will fracture. That is called as point E or fracture point. Is the graph clear for all? You want to see previous slide? Okay. Is there any doubt in this slide, or you just want to note down? Okay, so we will move on. So based on this graph, you won't get any numerical, but you will get conceptual question. Okay. So for some objects, you know that they are very malleable and ductile, which means they, like, their elasticity is good. Okay. So there are like two terms that you should know: elastic objects and plastic objects. Plastic doesn't mean the plastic we are using. Okay, it means brittle objects. There this region will be very, very small. Okay, so after their elastic limit they will suddenly break, like glass and all. They are very brittle. Why we mention them as brittle is because they don't have this plastic region much. Okay, they will break fast after the elastic limit. So such objects are called brittle objects. And comparison between like two different objects, steel and copper, like which is having more tensile strength, all those. Okay, such conceptual questions will come from based on this thing. Now coming to elastic potential energy stored in a stretched wire. Okay, so we know that there is some energy. That's why when we are elongating and releasing, it is coming back to original shape, right? It has some energy which is stored, potential energy stored in it. So for finding that, we will compare stretched wire. Okay, stretched wire with a spring. As you know, here Young's modulus is equal to F L A by delta L. This formula we got from previous slide. We know this. And for spring, if you are taking F equal to minus kx. Minus sign just means the direction of force. If you just take the magnitude, it is F equal to kx. Comparing with this, can I write F equal to what will come? A delta L y by capital L. So this will be the formula for F from stretched wire. Now if you compare this side by side, F equal to A y by L delta L. Delta is the L is the elongation. In here for spring, X is the elongation, right? So if you compare side by side, we can say that K equal to A y by capital L. Okay, one result which we are taking. Any doubts? Okay, now what we are going to do is, we are going to find potential energy of spring. Potential energy stored in a spring is half kx square. We just have to substitute our Young's modulus values for this. Okay, so x we can write as what? X, like x is delta L. If you want, yes, any doubt? Didn't understand. From stretched from Young's modulus equation, we have this, right? For a stretched spring, y equal to FL by A delta L. In this, I am equating F equal to this. Just cross multiplying, and I am getting a equation for F. I am comparing that equation of, equation of F with spring equation, spring restoration force equation, if you see, F equal to some constant into delta L. Here again some constant into X. So X is similar to elongation in spring. From mean length, if you are pulling, that extra elongation is X. Okay, and extra elongation in wire is delta L. So if these two are similar, then I can say that K equal to AY by L. Okay, we already know an equation for potential energy stored in spring. That equation is half kx square. Now we got value for k. If you get value for x also, you can substitute them both and get a formula for potential energy. X will be equal to, from this, if you consider delta L as x, you will get x equal to FL by AY. Okay, I am considering delta L as x. So delta L equal to this and F equal K equal to this. So half kx square will be half AY by L FL by AY the whole square equal to potential energy. Okay, is there any doubt in this? Till here, if you have any doubt, please ask. Okay, I am assuming that you don't have any doubt. Okay, so I am moving on. Now from here I will get so many things. Okay, like cancelling each other and additional like substitution and all, I will finally get that potential energy stored in a stressed wire equal to half into stress into strain into volume. Okay, this is the formula you will get. We don't need this derivation, we only need this formula. Potential energy stored in wire is equal to half into stress into strain into volume. But you will get some extra quantity called as energy density. Energy density is nothing but U by volume. Potential energy by volume is energy density. So what will be that formula? Energy density we will write as small ud. This you will get as half into stress into strain. This is the formula you should remember. Energy density equal to half into stress into strain. Ma'am, explain once from last second line. From here, this we are getting by like substituting so many things. I don't have that much space to write, that's why I did not write. If you are calculating this, you will get half AY by L F square L square divided by A square Y square. Okay, then F square, yes.
From that x is equals to FL by AY.
Okay. See, we are comparing these two equations, right? So, y equal to FL by A delta L. This is the formula for Young's modulus. Delta L is the extension or extra length, same as x. X is the extra length in spring, right? Like what is the extension in spring? That is x, same as extension in wire is delta L. So I can say that x equal to delta L. If you want to find delta L from this, delta L will be equal to FL by AY. Now understood? Okay. So by like cancelling is other things and all, we will get F square by A square we can write as stress square. Okay. Then we will have L square L cancel, y square y cancel. Then what do we have? A L by y. Area into length I am writing as volume. Okay. So this will become half stress into stress by y into volume. Okay. Now stress by y equal to stress by strain. So stress by y equal to strain. That's how we get this formula. Okay. I hope that is clear for all. Then energy density is potential energy by volume. So energy density formula half into stress into strain. Still anybody have any doubt regarding this? Okay. So we will move on to next one. That is viscosity. Okay. Viscosity, as you know, is a frictional force but present in fluids. Okay. In solids, the frictional force is normal friction only, and when that some resistive force which is present in fluids is called as viscosity. It will determine how fast something is flowing and all. As you know the difference between water, honey, ketchup, toothpaste, how easily it can flow. That will depend on viscosity of that liquid, okay, or fluid. Why we call fluid is because air is also a fluid. So gases and liquids have viscosity. Now there is something called as streamlined flow or laminar flow, and then other is turbulent flow. Streamlined flow will look something like this. So imagine you are opening a tap. Okay, when the speed is very very low, you can see it will move like a very smooth flow. That is streamlined flow. As you increase the speed of the tap, it will like twist and turn. That will be turbulent flow. So we know somehow, okay, it is depending on speed. Streamlined flow and turbulent flow depends on the speed. Okay, so that speed thing is called as critical velocity. Okay, so there is a maximum velocity for every type of fluid above which it will become turbulent flow. Okay, maximum velocity for which it can flow in streamline. If you increase velocity more than that, it will become turbulent flow. And this critical velocity equation you will get as k eta by rho r. Okay, in this k is Reynolds number. Eta is coefficient of viscosity. Then rho is density of the liquid, and r is radius of tube. Okay, radius of tube. Radius of whichever tube it is flowing, that is r. Reynolds number is a constant number for each individual liquids, like different. For water it is around like 1000, and for honey it will be different value. So honey it will be a higher value because its critical velocity can be high. So similarly, Reynolds number, if somebody is asking you to find, you can find from this. That is Reynolds number equal to critical velocity rho r divided by eta. So just like this. From this you are not going to get any numerical. From this there will be only conceptual question. Okay, there will be no numerical with these formulas. Is that clear? Is there any doubt regarding turbulent flow or laminar flow? Okay, so we will move to the next. That is coefficient of viscosity. Okay, if you are taking this, you know like how fluids are flowing. In the previous slide we saw that like this it is shown, right? Which means we consider layer by layer flow of fluids. Imagine this is the surface of the tube, and near to this the fluid will be slowest. whichever layer is flowing next to this fixed surface will be slow, and as we move away from it, the speed of fluid will get faster, layer will be faster. So there is a layer of fluid here at x distance from the fixed surface, and it is having velocity v, okay, and there is another layer at what distance, x plus dx distance, and its velocity is v plus dv. So when we moved dx distance, velocity increased by dv. So dv by dx is called as velocity gradient. Okay, this value is called as velocity gradient. So if you increase, like move to the next layer, how much velocity will increase, this will give you that value. And what is the viscosity is a force, as we told you, resistive force. What is the formula for that force? That will be, it will depend on the area which is in contact. So it will be proportional to area, it will be proportional to this velocity gradient, and since removing that proportionality we will get a constant, that is our coefficient of viscosity. Okay, it is the negative sign shown here is because since it is resistive, it is opposing the flow, that's why negative sign. Okay, so here area of cross section which is in contact, then sorry, not in contact, area of cross section of the tube, and dv by dx velocity gradient, eta is coefficient of viscosity. But our numericals won't be coming from this formula, it will be coming from next formula, that is Stokes theorem. Okay, if there is no doubt in this, we will move to the next slide. Okay, before going to Stokes theorem, we need to know temperature effect of viscosity, like if temperature increases or decreases, how viscosity will change. As you can see here, for liquids, okay, it will decrease with the increase in temperature. Temperature increases, viscosity decreases. So eta is proportional to 1 by root T for liquids, and for gases it is inversely proportional, which means it will be directly proportional. When temperature increases, viscosity increases. Okay, this is for gases. Is that clear? For liquid, if you increase temperature, viscosity will decrease, which means resistive force will decrease. For gases, if you are taking, when you increase temperature, viscosity also increases. Okay, in every situation we should include negative sign in the previous formula. No, it will depend on case by case. Like always it is a resistive force, it will be in like opposing the motion, but as you compare the formula with the answers option, if there is negative sign in the options, then you have to consider. If there is no negative sign in the option, you don't have to consider. Okay. So this is the temperature dependence of viscosity, different for liquids and gases. See, next moving on to Stokes law. Okay, Stokes law is applicable for a spherical object. Okay, it should be a spherical object moving with v velocity through a fluid. Okay, imagine we are throwing some ball or some spherical thing into the water. It is moving through water with v velocity. Then the opposing force, resistive force, because of viscosity, it will have is this. Okay, only one formula is there, F equal to 6 pi eta RV. Eta is coefficient of viscosity, R is radius of the object which we have thrown, and V is the velocity with which it is moving. You will get numerical from this formula only. Okay, they will ask what is the viscous drag. Viscous drag experienced by the object. Then it means that you have to find this force, this resistive force because of viscosity you have to find. Any doubts? Just note this formula. You have to by heart this formula. Is there any doubt? Okay. So we will move on. So last topic in this is terminal velocity. Another like major topic from which you will get numerical is terminal velocity. Okay. How we are getting this value is, see, Stokes law, this is resistive force happening, right? So when an object, let's say an object is falling in a like fluid medium, it can be like rain falling from sky, it is falling through air. Air is also fluid, I told you. So an round object, it is falling through a fluid medium. This object is having density rho, this fluid is having density sigma. In that case, it will have mg acting downwards, that we already know. Then buoyancy force, buoyant force acting upwards. Buoyancy is a concept we will learn in like fluid mechanics, but we don't need that topic exactly. We know there will be upward force, that is buoyant force. That's why some objects will float on the surface of water. Like if you put thermocol balls, it will not sink, it will be on the top. If you put stone, it will sink. So it depends on the buoyant force. Okay. And there is this Stokes viscous force acting upwards. So net force will be, but still it is falling downwards, right? F net will be equal to mg minus viscous force minus buoyant force. Okay. Terminal velocity occurs when this net force is 0. F net equal to 0. Net force 0 means acceleration not there, object will fall with constant velocity. That constant velocity is called as terminal velocity. Okay. When all forces cancel out, net force becomes 0 and the object will fall with constant velocity, which is called as terminal velocity. Like why that concept is there? What is Fv? Fv is the viscous force from Stokes law. Like because of the resistance in the fluid, there will be drag force, right? That drag force is Fv. Is that clear? Okay. So by how this concept came? Imagine raindrops, it is falling from like, let's say that like 2 km from the sky, above 2 km it starts. As it comes down, its velocity should increase, right, so much because of continuous acceleration due to gravity. You can just calculate the value. Okay, what will be the velocity of a raindrop by the time it reaches the ground. But if it is coming with that much speed and if you are standing in rain, you will be full of holes if the raindrops are coming with that much velocity. But it is not happening. Why? Because of terminal velocity. At some point, like there will be a resistive force in air resistance, that will cancel out mg and the velocity, like raindrop will have constant velocity. So it will fall with that constant velocity only, that is terminal velocity. By substituting this, we are getting this formula. Okay, mg, the formula will come as mg minus buoyant force equal to Fv. Like this you will get mg minus buoyancy, you will get V rho g, V into rho minus sigma g, mg minus buoyant force. This viscous force formula is this. Substitute it here and make volume equal to 4/3 pi r cube. Substitute all that, you will get velocity equal to this value. 2 by 9 r square rho minus sigma g by eta. In this already told you, sigma is density of the object falling, rho is density of the object falling, sigma is density of the fluid, g acceleration due to gravity, eta coefficient of viscosity, r is radius of the object. Is there any doubt in this formula? This one also you have to by heart. If you don't have any doubt, we can move to the problem solving then. Okay.
Ma'am, once again, can you tell me that what is rho and sigma?
Rho is density of the object falling. Okay. This object is having density rho. It is falling in some fluid medium, right? Its density is sigma. Okay. If sigma greater than rho, still you can substitute in this way only. If sigma is greater than rho, it will not sink. Okay. Like understood. If like density of the fluid is more than density of the object, it will float, it will not sink. Okay, so we don't have to calculate terminal velocity there. Is that clear? Okay. Next, coming to problem solving, let's start with this question. The maximum elongation of a steel wire of 1 meter length is if the elastic limit of steel and Young's modulus are given. Okay. So first we have to, whenever we are approaching the question, today we have time, so I will explain like step by step. Whenever we are trying to solve physics question, the proper method to do it, write down the given values. So first thing given is length of the wire. Length capital L is given as 1 meter. Next, elastic limit of steel and Young's modulus are given. Young's modulus we can directly write as 2 into 10 to the power 11 Newton per meter square. Okay. You see the unit of Young's modulus. It is Newton per meter square. Young's modulus equal to stress by strain, right? Strain is ratio of length, change in length by original length. So strain is a dimensionless quantity or unitless quantity. Okay. So stress is having same unit as y. Young's modulus and stress have same units. Okay. So the other thing given also Newton per meter square, elastic limit. So that is what? That is stress. Stress equal to 8 into 10 to the power 8 Newton per meter square. This is maximum strength that is given. So elastic limit is maximum stress. Stress we can calculate. Now what do you want to find? Maximum elongation. Elongation is our delta L. Delta L you have to find. Then y equal to stress divided by delta L into L. So from this we can find delta L is equal to stress into capital L divided by Young's modulus. All values are given in the question. Just substitute and find the answer. Did anyone get any answer?
Option B.
Are you sure it's option B? Did you properly convert the into millimeter?
Option A.
Yes, option A is the answer. Like check the units. Here we are calculating in meter. You will get the answer in meter, but we have to convert it to millimeter. Okay, option A is the answer. Next one. I hope there is no doubt in the previous question. Coming to next one. A metallic bar of Young's modulus the given value, and coefficient of linear thermal expansion. See, a new thing is coming. We are not going into thermal expansion, that's why I will cover it here only. Of length 1 meter and area of cross section this, heated from 0 degrees Celsius to 100 degrees Celsius without expansion or bending. Force developed. Okay, so this is from a topic called thermal stress. What is? Because when there is heat, like heat given to objects, there will be elongation in that object. Okay, when heat is given, then temperature increases, an object will increase in length. And how does it increase in length? Do you guys remember the formula for resistance dependence on temperature from current electricity chapter? Temperature dependence of resistance. You must have seen a formula like this. Yes, R naught 1 plus alpha delta T, right? Same formula only for length also. How length will change depending on temperature? You will get new length equal to original length into 1 plus alpha delta T. If you substitute this, you will get the value. Okay. So now coming to our Young's modulus part. Young's modulus is equal to force into L divided by A into delta L. We only want delta L. So new length is L naught plus delta L, right? This is original length, okay? L naught plus delta L. So delta L will be equal to what? From this we will get delta L equal to L naught alpha delta T. Substitute that here. So F L naught by A into L naught alpha delta T. L naught cancel. You will have F by A alpha delta T as equation for Young's modulus. Okay. Now what we have to find, we will see. Young's modulus is given, alpha is given, coefficient of linear thermal expansion, that is alpha. L is given, but we don't need that in the equation. Then area of cross section A is given. You have to find force. So F you have to find. F will be equal to Y A alpha delta T. Substitute all the values, you will get the answer. Anyone got the answer? This is Y alpha area of cross section delta T.
Option B.
B, are you sure?
Option B, ma'am.
Okay, let's see. Option B is the answer. Okay, so as you can see, option A and B are like close to each other, so you have to calculate the power of 10 properly, then you will get the correct answer. Okay, then coming to next question. I hope nobody has doubt in the previous one. Is there any doubt in this? No. Okay. Coming to next question. Amount of elastic potential energy per unit volume of a steel wire of length 100 centimeter to stretch it by 1 millimeter. Young's modulus is given. Okay. Amount of elastic potential energy per unit volume. Potential energy per unit volume, we got the formula, that is half into stress into strain. Okay, this is the formula we know. Let it be here. Let's see what are given things. length equal to 100 centimeter given, stretch it by 1 millimeter, so delta L will be 1 millimeter. Then y, length, Young's modulus is given as 2 into 10 to the power 11 Newton per meter square. From delta L and L we can find strain, but stress we cannot find, and nothing is given. But y equal to stress by strain, which means if you want to find stress, that is equal to y into strain. So we can substitute it as y into strain, that will be stress again multiplied by strain. Okay, so this will be half y into strain square. All the values are again given, just substitute and find the answer. See here, it is given in centimeter, it is given in millimeter, so convert it to SI units.
Option D, ma'am.
Option D. Everybody got that? Okay. Answer is option D. Like these are like very easy values only, so probably you should increase your calculation speed, okay, to get the answer. If it's done, then we will move on to the next question. Next one, it is a conceptual question, so we must attend it. Which of the following statement is not true? We have to find a false statement. First statement, coefficient of viscosity is a scalar quantity. Second, surface tension is a scalar quantity. Third, pressure is a vector quantity. Last, relative density is a scalar quantity. Which do you think is wrong one? Yes, very good. C is the answer. Why? Pressure, even though direction and magnitude is there, it doesn't obey laws of vector addition, so it is not a vector quantity. Okay, so that's why that is the wrong option. Is that clear for all? Okay. Coming to next one, viscous drag acting on a metal sphere of diameter 1 millimeter falling through a fluid of viscosity 0.8 Pascal second with a velocity of 2 meter per second. As I told you, if viscous drag is there in the question, what you have to find? Stokes law force. Okay, Stokes law, from that we will get the force. So 6 pi r eta v. This is the viscous drag that you have to find. See, diameter is given as 1 millimeter, so radius will be half millimeter. Okay, eta is given as viscosity 0.8 Pascal second. You can find the unit. This is the SI unit for it. And velocity is given as 2 meter per second. Substitute all. Option A. Okay. Is everybody got that value? Direct substitution only. So that is the like plus point about these chapters. There will be direct formula questions only. There will be no twist and all. Okay, option A is the answer. I hope we can move to the next question, and there is no doubt in this. Okay, next one. Let a wire be suspended from the ceiling and stretched by a weight W attached at its free end. Longitudinal stress at any point of cross sectional A. You have to find longitudinal stress. Can you tell me the answer without my help? Okay, weight is mg force. Okay, weight is nothing but like a wire is suspended. Yes, correct. Okay, mass m is hanging, so mg force is acting. Area of cross section is given as A. Mg equal to weight. So stress is nothing but what? Force by area, that is W by A. So option A is the answer. I hope everybody got that. Is there any doubt? Okay. Moving to next one. Terminal velocity of a copper ball of radius 5 millimeter falling through a tank of oil at room temperature is like this is velocity. Viscosity is given as this, and you have to find viscous drag force. So again formula is same only, force equal to 6 pi eta RV. Direct application, substitution. Just don't forget to convert this into meter and this also into meter. Option B. Okay, that is the correct answer. Like if you properly substitute all the values, you will get the correct answer. There is no other things in this question to discuss. Okay. Next one. Here they are talking about a spherical ball is dropped in a long column of highly viscous liquid. Curve in the graph shows speed of the ball as a function of time. So what will be speed of ball with respect to time? From starting you have to find what will be the speed. Which, yes, correct answer is B. As you can see, when we drop the ball, initial velocity is 0. As it falls, like because of mg, its velocity will increase. Then it will reach a maximum point, then it will stop. That is terminal velocity. So this graph is the correct answer. Okay, B. I hope everybody understood that. We will move to the next question then. Did not understand. Like if you drop something, because of mg, acceleration due to gravity, its velocity will increase, right, from 0 to a maximum value. That maximum value is terminal velocity. Once it reaches terminal velocity, then it will move with constant velocity. So from 0 increasing, then reaching terminal velocity. That's how. Is it clear now? Okay. Coming to next assertion reason type question. The assertion is stretching of a spring is determined by shear modulus of spring. A coil of copper spring has more tensile strength than steel. Can you tell me if A is true or false?
False.
No, actually A is true. Even though elongation is happening, it is spring shape is changing, right? Here longitudinal means it's a straight thing, we are elongating it. Spring, it is like twisted thing. With elongation means its shape is actually changing, which means it will depend on rigidity modulus. Shear modulus is same as rigidity modulus. A is true. But steel has more tensile strength than copper. That's why we use steel in buildings and all instead of copper, right? More we are using steel. So A is true and R is false. This is the answer. Understood? Is there any doubt? Okay. Oh, sorry, I showed the answer in between, but let's see. The velocity of a small ball of mass m and density d when dropped in a container filled with a glycerin becomes constant. Density of glycerin is d by 2. Then viscous force acting on the ball. We took Young's modulus. Finding energy density. Okay, I will explain it. First do this, okay? Okay, mass of the ball is given, density of the ball is given, then density of glycerin is given, viscous force acting on it we have to find when velocity becomes constant. As I told you, in this case, like mg minus viscous mg minus buoyant force will be equal to viscous force. I told you this while deriving terminal velocity, right? And this side is nothing but volume into rho minus sigma into g. This will be our viscous force, okay, at terminal velocity. From the given values, try to find if you can find the answer or not. 1 second. Okay, so what we need is this. Rho is given as d, density of the material. Sigma is given as d by 2. So rho minus sigma we already have d by 2. Okay, so this will become d by 2 g. Now volume is not given, density and mass is given. So volume equal to mass by density. So density equal to mass by volume. So volume equal to mass by density. Substitute that, V equal to m by d, you will get mg by 2. This is the answer. Okay, is there any doubt in this one? Okay, now I will explain about that potential energy. There we are not taking spring, okay, we are considering that a wire stretched will behave as a spring elongated. Okay, we are comparing wire stretched only, we are finding potential energy stored in wire, not in spring, but we are comparing them and finding a formula for that. Okay, for deriving the formula we are comparing a stretched wire to a spring. Okay, we are not finding for spring. I hope that you understood that. Okay, so answer is mg by 2. Next one, a wire of length L and area of cross section A are hanging from a fixed support. Length of the wire is changed to L1 when mass m is suspended at the free end. Expression for Young's modulus. Okay, wire has length L, area of cross section A. Now when mass m is hanged, length becomes L1. Okay, you have to find equation for Young's modulus. Young's modulus formula is FL by A delta L. Now compare and find which is the answer. Yes, option C is the answer. L1 is not change in length, L1 is new length. So delta L will be L1 minus L. Okay, don't make that mistake. I hope everybody understood this. Okay. Moving on. There is a small sphere of radius r falling from rest in a viscous fluid. As a result, heat is produced due to viscous force. Rate of production of heat when the sphere attains terminal velocity is proportional to what? So actually we need to know one more formula for this. If force is given, power is equal to force into velocity. Okay, force into velocity will give us power. Power and energy are related to each other. How? Power is equal to energy by time. So if you can find power, you will get energy. Here energy is heat energy. Okay, because of friction heat is produced, right? Similarly, because of viscosity heat is produced. So you just need to get what power is proportional to r to the power x. This you have to find. Viscous force we already have 6 pi eta r v into v. Okay, and this is given as a terminal velocity. So at terminal velocity 6 pi eta r terminal velocity square we have. So if we are only taking proportionality, p proportional to r vt square, what is the equation for terminal velocity? Vt equal to 2 by 9 rho minus sigma r square g by eta. This is equation for terminal velocity. Terminal velocity square means p will be proportional to r into r to the power 4. So proportional to r to the power 5. Answer is option C. I hope there is no doubt in this. Is this clear? Whenever heat we are talking, it is an energy. So we need to connect to an equation with energy. From force and velocity that is given in the question, we can find power. Power is energy by time. So that's how we can relate force and velocity to heat energy. Okay. I hope this is clear. Answer option C, r to the power 5. Moving to next question. Two wires are made of the same material and have same volume. First wire has cross-sectional area A and second wire has cross-sectional area 3A. If length of the first wire is increased to delta L by applying force F, how much force we have to use for second wire to have same delta L? Okay, so first wire, length L, area of cross section A, area of cross section A, applying F force, it created delta L elongation. Both are made of same material, which means Young's modulus is same for both. So in this case, Young's modulus is equal to FL by A delta L. Okay, we have to find the force applied in second one. Okay, so there also Y is same, some new force is there, initial length L, area equal to 3A, and we have to create the same elongation, which means delta L is same. Okay, comparing to this FL by A delta L, we can cancel out these things and we will have F 3F equal to F dash. Right? No, sorry, have same volume, not length. Sorry. Okay, both material have same volume, which means length is different. Here volume equal to L into A. Here also volume is same, which means 3A into some L. Okay. Comparing, we will get LA is equal to 3AL, AA cancel, L by 3 equal to next L. Okay. Did someone put the answer? Yes, C is the answer. Okay. So here Young's modulus, if we are finding F dash small l divided by 3A into delta L. This is equal to FL by A delta L. Substituting here F dash L by 3 into 3A 9A delta L equal to FL by A delta L. Cancelling out these things, we will have F dash equal to 9F. Okay, answer C. Is there any doubt? Okay, so we will move to the next question. Okay, coming to bulk modulus. Bulk modulus of a spherical object is B, subject to uniform pressure P, fractional decrease in radius. Fractional decrease in radius, you have to find delta R by R. This is relative change in radius or fractional decrease, we can say. See if you can find it or not. We have bulk modulus formula with respect to pressure and volume. Volume we can relate it to radius, right? So like that you have to find. Okay, bulk modulus is equal to PV by delta V. Okay, now V is equal to 4 by 3 pi R cube, initial radius, or small r we can use if you want, R cube. New volume will be V plus delta V, that is equal to 4 by 3 pi R plus delta R the whole cube. Right? Then if you expand this, you will get 4 by 3 pi R cube plus 3 into 4 by 3 pi R square delta R. Then next term will be 3 into 4 by 3 pi R delta R square plus 4 by 3 pi delta R cube. See, in this what we will do is, delta R is a very small quantity. It will be like 0.01 or something. If you take square and a cube of those, it will be very small values. So this term and this term we are neglecting. So delta V plus delta V will get as 4 by 3 pi R cube plus 3 into 4 by 3 pi R square delta R. This is V plus delta V. From this you can find delta V also, then we also substitute, find delta R by R. Okay, so V equal to 4 by 3 pi R cube divided by delta V is equal to 3 into 4 by 3 pi R square delta R. So 4 by 3 pi cancel, R square and this cube cancel. We will have P R by 3 delta R equal to B. We have to find delta R by R. So that is equal to, nobody is answering. Are you guys even doing the problem? P by 3B is the answer. Is there any doubt in this formula or solution? Are you guys listening and solving the problem? I can't understand. Okay. Nobody has doubt then. Okay. We will move to the next question. This one, Young's modulus of steel is twice that of brass. Two wires of, so Young's modulus of steel equal to 2 times Young's modulus of brass. Two wires of same length, same area of cross section of steel and brass are suspended from the roof. We want lower ends of the wire to be at same level, then weights added to the steel and brass should be of the ratio of. So both have same length, same area of cross section, but a different Young's modulus. Okay. We are hanging some weight M1 here, mass M2 here, and final length should be same. Delta L should be same. Delta L have equation that is equal to FL by AY. This should be same for both, so we can say force 1 L A by Y1 will be equal to force 2 L A by Y2. Okay. L A will get cancelled. You will have, just substitute now force of steel divided by Young's modulus of steel equal to force of brass divided by Young's modulus of brass. We want ratio of weight of steel by brass. So we want the equation for F steel by F brass. What will be the answer? Yes. So are you sure it's option C? Is it not option? Yes, option D. Option D is the answer. Okay, option D is the answer. Is there any doubt in this question? Can we move on to the next question then? Okay. Sorry, actually this is the last question. So first time we are ahead of time and we completed all the questions in the class itself. I hope you guys understood the whole concepts. If possible, try doing more questions also, and remember the thermal stress. Okay, elongation, expansion due to temperature, that formula also please remember. And if there is any other doubt, you can contact me, and now you can go and take rest for like next 35 minutes. 12 o'clock there will be chemistry class. Please join for that. Thank you.